In classical computational algebra, when an algebraic system is parameterized, so its geometric shapes cannot physically intersect in real Euclidean space, the system evaluates to an empty set. The resulting complex roots are routinely discarded as computational noise, or numerical overflow. The theory of infinity framework operates on a different axiom. Operational mathematical energy cannot simply vanish. Instead, reality and structured systems emerge ex totalitate, extracted and carved out from an all-containing indeterminate totality. When a strictly restricted real spatial boundary rejects a continuous mathematical trajectory, that geometric tension triggers a boundary event. The underlying mathematical energy is violently ejected into the complex plane. Rather than treating these complex phase roots as a mathematical dumping ground of chaotic overflow, this framework proves the ejected mathematical mass is highly structured and precisely measurable. The intimidating computational debris found in complex phase space actually functions as a perfect, unyielding topological mirror, preserving the exact geometry of the real space boundaries that rejected it. We define these highly structured real-world origins as a golden set. This is a foundational, internally coherent geometric boundary that encapsulates an intelligible, lawful mathematical system. When we push an algebraic system past its absolute spatial limit, we create a strict exclusion zone. The real space is completely restricted, forcing the active system to eject its metric mass. By rigorously decompiling these specific boundary ejections, we can extract pristine invariant signatures of the golden ratio, or phi. We will audit two extreme algebraic boundary collisions to trace this exact mechanism and definitively prove the theorem of complex phase conservation. Mapping this conservation mechanism identifies specific, repeatable geometric signatures within the complex plane. Our objective is to evaluate whether the imaginary plane functions as a structured topological mirror of the real space boundaries. System 2 constructs a forced algebraic collision between two fundamental manifestations of the discrete Fibonacci sequence, a linear boundary and a quadratic elliptical boundary. The linear trajectory is governed by lighter Fibonacci sequence rungs, 89 and 55. The bounding ellipse uses heavier, deeper rungs, 144 and 89. Because the linear trajectory bypasses the restrictive ellipse within Euclidean space, a real plane intersection is impossible. The underlying computational logic attempts to resolve the rigid algebra, fails in real space, and violently spills the coordinates into complex phase space. Standard computational algebra systems output the resulting root coordinates as a chaotic spray of massive 8-digit integers and heavy floating point radicals. To evaluate this, we apply apophatic decompilation. This strict analytical protocol strips away the numeric noise and scalar camouflage masking the true algebraic relationships. We isolate the specific topological mass rejected from the real plane by extracting the absolute magnitudes of strictly the imaginary components. This chart shows the exact extracted absolute magnitudes of those imaginary x and y roots. The unfathomable radicals collapse entirely, leaving pristine Fibonacci rungs of 89 and 55. Dividing the x magnitude by the y magnitude yields an exact geometric aspect ratio of 1.618. The massive fractions and integers flawlessly annihilate one another. The imaginary plane perfectly preserves the exact 89 to 55 golden set boundary that initially seeded the system.
System 3 shifts the spatial constraint, transitioning away from a closed, encapsulating elliptical envelope to an open geometry of parallel parabolic shells. Two parallel parabolic equations are constructed, once again mathematically anchored to the identical absolute spatial limit. Crossing the assigned Fibonacci rungs generates a highly negative determinant for the system's coefficient matrix, causing a structural topological collapse. This extreme mathematical distortion violently forces the x-coordinate entirely out of the real plane and into pure imaginary space. Conversely, the y-coordinate is not ejected. It remains statically bound within the metric plane, manifesting as a heavily positive, purely real scalar. In classical geometry, attempting to directly compare a purely imaginary vector to a real scalar coordinate is an incoherent operation. We resolve this by applying the transdimensional bridge protocol.
We evaluate the proportional weight of the spatial coordinates through magnitude normalization. This chart normalizes the absolute magnitude of the purely imaginary x root against the square root of the real y root. The massive anchors wash out, leaving a pristine fractional footprint of 144 over 89, resolving exactly to 1.272.
Imaginary escape channels do not drift randomly. They remain permanently tethered to the real metric plane by exactly the square root of the golden ratio. We have observed that topological geometry is perfectly conserved when forced into the complex plane. The physical problem is one of reversibility. By what exact mathematical mechanism can this massive complex energy be pulled back into the real plane? To answer this, we must first audit the specific source of mathematical friction that triggered the violent complex ejection in System 2. The system creates extreme topological pressure. The heavier Fibonacci sequence constraints of 144 and 89 are applied to squared higher degree terms. This dense bounding box physically crushes the linear trajectory, which is governed by lighter constraints. The continuous mathematical manifold simply cannot sustain the tension of heavy mass pressing down on an exponential curve, while lighter mass attempts to traverse it linearly, causing the geometry to shatter. These complex ejections are not terminal failures of polynomial algebra. They are highly specific, completely reversible topological stress states. The formal mathematical mechanism required to reverse a catastrophic ejection is called the Octic Parity-Inversion Lift. This requires a deliberate architectural flip. The lighter coefficients are intentionally reassigned to the highest degree terms, and the heavier coefficients are assigned to the lower degree terms. Applying a fourth-degree lift scales the system from a quadratic base to an octic bounding shell. This squircle geometry snaps violently back into real space. Because the heavy mass now sits on a slower-growing algebraic parameter, the tight, dense bounding box expands, and the topological pressure is completely relieved. Relieving this pressure forces the ejected mathematical mass completely out of the complex plane, effortlessly yielding exact real anchor points in a localized two-dimensional plane. In both the ellipse and the squircle, the continuous complex phase is dictated by the discrete integer boundaries that enclose it. These results show that topological mass is perfectly conserved and reversible, even when forced out of the real metric plane.